Hi, so I am going to be talking about prominences, which are condensations of coronal plasma, which form on closed field lines, like the dark orange blob in this cartoon. And I'm interested in them as a mechanism for mass loss for young and rapidly rotating stars. And specifically here, I'm talking about M dwarfs. So you know where I'm going in the next 10 minutes. I am going to show you that prominences could have comparable mass loss to the stellar wind. So these plots are going to come back later in the talk, so I'm not going to go into too much detail just now. But the plot on the left shows the mass loss rates from the wind, and I've taken this from the literature. And on the right, this plot is from this work with the modeled prominence mass loss rates. The new information on this plot is the black points and the blue dashed line, and the other lines are the same as the lines in the left-hand figure. And the point really is that the prominences and the wind are quite similar. So these stars have a thermally driven outflow of material, which is their stellar wind, and this flows from the surface along open field lines. And these winds are responsible for removing mass and angular momentum from the star, which causes the star to spin down as it evolves. You can easily observe the solar wind. Satellites can measure it in situ, but for cool stars, measuring their winds is very difficult due to their low density in most parts. But the winds influence how the stars evolve, and the plot here is an example rotational evolution plot showing the stellar rotation rate, which is the y-axis, against age, the x-axis. And at some point in their lives, the stars start to spin down due to the angular momentum that's being lost. And exactly how depends on the initial rotation rate of the star. So the blue line here are the fastest rotators and the red, the slowest rotators. But the point is that they all show similar behavior. And the theoretical models rely on the wind to provide this spin down, but they do tend to underpredict the rotation rate of stars later in life when compared to the observations. And to make the models converged to observed values, a scaling factor is often added. And this scaling factor is synthetically removing angular momentum from the system. A question then is, what could this scaling factor represent physically? This is the plot of the stellar rotation rate against X-ray flux of the star, essentially stellar activity levels. And the red, blue, and green points are various observations of stellar wind mass loss from different methods and different studies. And whilst there is a correlation, there is quite a large amount of scatter. What I want to know is, using our models of prominences, what would the prominence mass loss rates look like? And as I've already kind of showed you, the answer is that they're similar in magnitude, and we also have a lot of scatter. Taking a step back and away from the winds onto the prominences, I mentioned at the beginning that a prominence is a condensation of plasma and that it's supported above the surface by closed magnetic field lines. We see them on the sun, but on rapidly rotating stars, prominences are much larger in mass and extent than they are on the sun. And they're observed in H-alpha spectra. So here's an example of that on the right-hand side from the star AB Doradus. The y-axis is rotation phase of the star, which is essentially time, and the x-axis is wavelength. So because the star is rotating, the H-alpha line gets broadened by the Doppler effect. So we go from one singular wavelength to a distribution. And so this axis is essentially position of on the stellar disk. And the color of this plot is intensity. So the black smudges are places of low intensity, so there are absorption features. And these are caused by the prominence passing in front of the star and blocking out light. So this is how we see prominences on these stars. They're formed by material that flows up the foot points of closed loops, and it then condenses. This is essentially like the stellar wind, only it's happening on closed field lines instead of open ones, and they can sit around for quite a few days, but eventually they become unstable, which can lead to them being ejected. If they're ejected, they're going to remove mass and angular momentum with them. And yeah, this is similar to a wind that kind of stops and starts as the field lines close and open again. To model the prominences on our M dwarfs, we started with the observations of the surface magnetic fields of the stars that we got from some collaborators. So these are the ZDI maps, or Zeeman Doppler imaging maps, for those who are familiar. There's an example up here in green and blue showing the field strength. And once you have that, you can extrapolate what the field would look like in the entire corona to get the full field lines, like in the plot below. With this, you can then calculate the stable points. So I've shown them in purple on this picture. And this is the locations in the field where material would pool and collect and form into a prominence. The total mass that can be supported at that point is then the mass of the prominence. So the red blobs on here are kind of showing like an example of where the mass is. The total mass loss from the prominences on a given star is just the sum of all the individual prominence mass losses. And this is calculated by using the prominence mass and its lifetime. And its lifetime is the time that it takes to supply that material to the stable point by a thermally driven wind. The angular momentum loss rate can be calculated from this too, using the mass loss rates and also the location of the prominences as well. So RP and theta are the radius to the prominence and its latitude. Here are the mass loss rates that we calculated then for the M dwarfs based on the modeled prominences. So these are the black points. The blue dashed line shows the line of best fit for these points. And the other lines are the published wind relations that I mentioned earlier. So the prominences show a very similar relation to the wind. It's almost directly on top of one of the wind relations. And there's still quite a lot of scatter, as we saw in the wind plot too. And the take-home message really is that the prominences for these young and low mass stars could remove significant amounts of mass and angular momentum. So they could be influencing the evolution of these stars. But currently prominences aren't included in stellar evolution models. So perhaps they could be the missing factor from these models that could help to remove the extra angular momentum, that scaling factor that I talked about. So this is all published, so you can go and read the paper if you're interested. It's on arXiv and you can get it from monthly notices too. So yeah, you can either scan the QR code or I've also linked the DOI to the paper here as well. So yeah, thank you.